for today's lectures is that we're gonna prove that earlier we already studied a little bit deep about HT. So today we're gonna show that HT of x, y uh, is Lipschitz in x, y, uh, you know, uniformly for t greater than equal to sigma greater than 0. So here by that I meant that, we need to stay with some certain time sigma, bigger than 0, then we are saying that the function ht is going to be Lipschitz uniformly, provided that t is big. Okay, so that's something that is quite important, and I'll tell you about certain implications as we go. And then the second point that I'm gonna just give a sort of real discussion on the depending on the names, this fatty calls lax or lignic or like semigroup. Okay, and then in other contexts, this is simply called on the optimal control formulation. Okay, so that's our goal for today. And to do so, then of course I need to recall certain points that we already discussed earlier. And I'm gonna go in a gentle way. Our first object of sort of discussion today is the function ht. Again, it's just going to be the minimum cost to go from x to y in a fixed amount of time t that is given to us, right? We go from here to here. And last time we already made a remark that if t is tiny, then of course you can see that even just in this illustration I'm drawing for going from x to y, if you go even just in a straight line connecting the two, then still, I mean, if you go like this, then the in the constant velocity then okay, then if we connect x to y uh, by a constant speed line segment, then the velocity is y minus x over t, right? And this blows up as t goes to 0. And you see that that's one of the reasons why that if we try to connect x and y rather suddenly, then the cost is going to be steep, right? Because I mean, if we do it this way in a constant speed line segment, so maybe let's say that this line segment is eta, then you see that the cost integral from 0 to t of L of eta s, eta dot s ds. Again, it's just a constant in eta dot, right? So you can compute, you can write a integral from 0 to t. L of eta s is something I'm not worried about. Eta dot s is y minus x over t. And you see that, again, because L is superlinear, this one goes to infinity as t goes to 0. Okay, so that tells us that, we got to be careful if the time is getting small. But if t is greater than equal to sigma greater than 0 for some sigma greater than 0 fixed, then we wouldn't encounter this issue, right? I mean, that's what we already discussed last time, but I'm just recalling it in a sort of brief way here. Okay, So now let's recall quickly the results, and we're gonna use some of them today. Um, you know, the first property, the boundedness of HT from below is obvious. Uh, the last property I already said that we have an extreme curves, a minimizer, which is CK. It's not obvious, but that's important. We prove it. Um, the third property is also simple because of the fact that we know already if U is bounded by L plus C, then that's going to be the case. The second one is actually one of the most important one. Uh, we're gonna use it a little bit today. What it tells us is that to go from X to Y in a time T plus T prime, then you always have to sort of go through some point in the between, which is Z, which is gamma T here in this case. And it turns out that, to go in an optimal way from X to Y, if you connect the dot at some point Z, you also need to go in an optimal way. So that is exactly, again, last time we talked about that. That's dynamic programming principle, and it's H of T plus T prime X Y is the optimal one going through Z. And again, as I said, we're gonna play with it a little bit today. Not a lot, but a little bit. Okay. So that's the first point that, I would say that this is one of the important point. It's a new point that we would need to use today. The second point that is also of interest, that we prove is also that, okay, I mean, the lemma, right? We say HT is bounded from above by some constant CT. That's not a big deal. Okay. What is really important is that, not just that it's bounded from above, but if I have certain level sigma greater than 0, as I said, then, if t is greater than sigma, then we see already from the example, right? In this example here, if t is tiny, then your velocity gets to be really big to connect the 2 points, right? But if you know are allowed to go in some time that not too small, is bigger than some fixed constant, then it's a very natural thing to expect that we have the red box I'm putting here on the left panel. Then your minimizer gonna go with certain bounded velocity, and the velocity, the constant k sigma, only dependent on sigma. It's not dependent on any time, right? So what is really important is that second point is that, uh, for t greater than equals to sigma greater than 0, this is given, right? Given, then then what every minimizer minimizer gamma has bounded velocity, uh, k sigma, which is dependent only on sigma. Okay. More precisely, we have gamma dot of s less than equals to k sigma for all s in 0t. So this is the second important point, and these 2 points together are the new points that we observed from last lecture, and we gotta use them today, to study further about the property. As I said, because we have more time, so we are doing things slowly, naturally, and I really enjoying doing it this way because I would have time to explain to you more of this theory. I mean, it's going from, the classical aspect to also that more like modern aspect, and based upon the second result here, that we have bounded velocity, we now can say that, okay, so for this sigma greater than 0 is fixed, we have the theorems that ht mapping from the torus, across the torus to R is Lipschitz, and t greater than equals to sigma is Lipschitz in both variable, in x and y, with the Lipschitz constant less than equals to some c sigma. Okay, and c sigma depends only on sigma, not on t, right? So it's again, it's remarkable that ht is Lipschitz, right? And the Lipschitz constant, it's dependent only on sigma. And again, I mean, this is sort of certain regularizing property that it's gonna come into place later. So later on, we're gonna use whatever we have developed here systematically, and we're gonna use the fixed point theorem to prove, or some fixed point theorems, depending on what I'm gonna try to do, to prove that we have existent Wickham solution. So that's remarkable. And it goes in a very natural way, right? We are just trying to analyze it, and it turns out that to do so, we would need the fact that the velocity of our optimizer, of our minimizing curves, are bounded. Okay, so let's do that. And you can already see that, I mean, the picture is pretty clear. Before getting really into the details, let me just explain to you the sort of like the how to put it, the original ideas, and then okay, it takes some time to write out the proof, but I wouldn't be too worried about that. So you have, this is x, this is y, right? This and then you have, this is x bar, this is y bar, right? And we want to show that ht of xy minus ht of x bar y bar is less than equals to c sigma x minus x bar plus y minus y bar. Okay, so that's our goal. Again, I'm writing down precisely what we need to show first, before getting into the details. And a natural way is essentially sort of, like to compare things, right? Going from x to y, for example, you can go in certain curves like this, that whatever, and then you are gonna use the fact that you can, use this given curve. Um, how to put it? Uh, yeah, I'm trying to find the best way to write this one down. Yeah, okay, so let me use gamma. I'm not using something too different because I don't want to conflict with what I'm writing on the left panel. Okay, so you're using, so you have connect x to y, you're using the curve gamma, right? And then you try to connect x bar to y bar by using some sort of like some modification of gamma. Okay, so that's a very natural thing to do, right? Now, the problem is that if you're trying to do that for any general gamma, the problem is that gamma, if we choose any arbitrary gamma, then it can go with very bad speed, right? Gamma can go sort of like very fast at the beginning, it can travel really, really quick here, and then slow down a lot in a middle segment, and then again travel really, really fast here near the end to reach y. So the problem with considering arbitrary curves to connect x to y might not be a clear cut for us to do comparisons, right? And what is really important was, earlier we already proved that if you choose an optimal gamma, right, if you choose a nice gamma that is a minimizer, or the minimizing part that connecting x and y, we know that its velocity is bounded, right? And when its velocity is bounded, everything is pretty much under control. And that's sort of one of the essential points that, again, it's by no means easy, right? It took us a lot of time to prove that there's a minimizer and connecting between Lagrange and Hamiltonian framework to prove that the velocity is bounded. But now, because of that, I can say that, okay, basically I can take gamma nice with bounded velocity. Okay, so that is a big thing, right? And once we know that, okay, we see that because it has bounded velocity already, I can change things a little bit here and there. It's not gonna change things too much, and that's sort of essentially the point. Okay, and a natural idea would be that I can sort of bridge the two things together. I can sort of select a point here. Maybe I'm going, epsilon is something like sigma over 4. So I give it a bit of amount of time. And then I try to bridge, x bar to something in the, in gamma epsilon here. Uh, So gamma epsilon, which is sigma over 4, because I know that if I only allowed it to connect in a very short amount of time, I would have to pay a lot of price, right? So I need to give it certain time to reach there. And then also similarly, I can go connect from here to gamma t minus epsilon going to down to y bar. Okay, and then you can see that we can try to design all various possible choices of gamma tutor. And I wouldn't say that there's only one choice, but a natural choice for us to do that is just to take a linear combinations of gamma and a line segment, right? Because that's sort of a very natural and simple way to connect the dots, and that's exactly what we are doing. Okay. So I would say that we really would need that, we really need nice bounded velocity of gamma. Okay. Right. So now let's have a look into the writing on the left panel that I wrote down here. Okay. I chose epsilon to be sigma over 4, and we designed gamma theta to be, again, you take gamma s and you take a linear combinations with a line segment connecting from 0 to x bar minus x, right? So you see that at 0 gamma, so at 0 gamma theta of 0 equals to gamma 0 plus epsilon over epsilon x bar minus x. So this is exactly x bar, right? So and at the end point epsilon, you have gamma theta of epsilon equals to gamma of epsilon plus 0, right? So epsilon minus epsilon over epsilon x bar minus x, so which is exactly gamma epsilon. So it's just a very simple trick of using linear combinations to connect the 2 points. And similarly for the second piece, that we are also combining gamma with a again a line segment connecting from 0 to y bar minus y to have the second piece, right? So the first piece is this one, the one I'm highlighting on the left panel, and the second piece is the other one I'm highlighting also on the left panel. I'm sorry. So that's exactly that. And now we can compare the values, right? We can, so did I write down here? So, okay, so I should have written it down a bit carefully, but okay. So basically, I should say, in a better way, that I take gamma to be exactly a minimizer, right? So I should have right away that ht of xy is just exactly the action function on gamma. So this is a better way to write down. And then I have gamma dot is about L infinity is bounded by K sigma. That's much better. And then because I'm choosing gamma to be like that, right? So I can control that ht of x bar, y bar. This is less than equals to integral from 0 to t L of gamma tilde dot ds. So from this one, we can see that we can control what is ht of x bar, y bar minus ht of xy is less than equals to just the difference of the action functional, right? Okay, so that's a better way to explain this point. So I have that difference, and you see that clearly the difference, you only have to account for the integral from 0 to epsilon and the integral from t minus epsilon to t, right? So that's only the two things that we need to, uh, we need to take them into account. Okay. And because they are more or less symmetric, so we can just control them. Um, so I only need to control one of the integral, and maybe let me write down so that you see. So only comparing um, the integral from 0 to epsilon L of gamma tilde dot minus L of gamma dot ds. Okay. And again, the so you can write this one down explicitly. This is integral from 0 to epsilon L of gamma tilde. Again, you can recall the formula up here, right? So you're just taking gamma s plus epsilon minus s over epsilon of that. um, so gamma s plus epsilon minus s over epsilon multiply with x bar minus x. And when we take the derivatives, we have gamma dot s uh, minus x bar minus x over epsilon minus L of gamma dot ds. Okay. All right. So again, it looks a little bit complicated, but you see what's the difference. You have this one is a difference in the positions, and this one is a difference in the velocity. Okay. Um, what is clear? What is the clear point here is that gamma dot here, they are bounded by k sigma, right? And because they are bounded by k sigma, so I have that the function is globally Lipschitz, okay. Not I mean because L is locally Lipschitz, but because the velocity now is bounded, right? So you see that what was written here is clearly very easily bounded by c sigma for some constant depending only on sigma of the difference in the position epsilon minus s over epsilon x bar minus x, and the difference in velocity 1 minus epsilon x bar minus x. Okay. So let me emphasize, I only have c sigma here uh, because I have that gamma dot is bounded, right? If gamma dot is arbitrary, if it goes to, like near infinity, then I wouldn't be able to control it so well. Okay. And, we are done, right? Of course, it's dependent on epsilon, but remember that we chose epsilon to be sigma over 4. So you can just replace this one by something like this is less than equals to uh, c sigma, epsilon is sigma over 4. So let's say c sigma uh, over sigma, something like that, x bar minus x. So it's really Lipschitz there, right? So you can modify this one to be another constant. So c sigma tilde or something x bar minus x. Okay. And similarly for the other integral, we have, and I'm changing the constant again back to c sigma. Again, the constant is changing line by line. Forgive me about that. But then eventually, by doing so, we can conclude that uh, ht function is Lipschitz in both variables, right? So that's pretty much it. Um, so we conclude that ht of xy minus ht of x bar y bar less than equal to c sigma x. I think I made a mistake. X minus x bar plus y minus y bar. Okay, there's a typo here. And actually the way, oh, x minus x bar. Minus y bar. And actually the way I'm writing here on the left panel is not 100% precise. I should have said, take the inf over gamma at the beginning. I should have said that. I mean, I thought that in my mind, but when I'm writing, it goes in the reverse way. I should have said from the beginning that I chose gamma to be the minimizer, a minimizer to start with. Okay, because by choosing so, I have that the velocity is bounded from the beginning. Okay. So any questions or any points you want to discuss with me up to this point? Or tell me if it's too trivial or something. I don't know. Many of the times that people in the literature, sometimes that they gloss over this point. Uh, I mean, sometimes, right? Not always. That there are certain points that we would think that is easy, and we would just like assume that it's obvious, and sometimes we could make a mistakes here, because if we look at the function ht, we can say, wow, it looks nice, it should be Lipschitz all the times, but it turns out that there are very tiny details that it Lipschitz, but the Lipschitz constant really depending on the lower bound of t. And as a matter of fact, you know you can actually prove that by writing down simple arguments. You can actually prove that the Lipschitz constant blows up when sigma goes to zero. So in other words, if we are not careful, if we claim that we have certain uniform Lipschitz property for all t, it would go wrong. Okay. So that's exactly the point of the remark here, that I would say right away, that warning, that c sigma goes to infinity as sigma goes to zero, and as a matter of fact, htxy is not uniformly Lipschitz in xy as t goes to zero. Okay. um of course, the bound that we recall and things like that was already clear. But the point of this important result is that once we treat the fact that t is small nicely, then what is really important is that we have a uniform bound, uniform Lipschitz constant for all t greater than sigma. So we can let t goes to infinity, for example, we still have this global Lipschitz estimate. Okay. And uh, okay, and again we have that. Yeah.
Oh, sorry. Could I just ask if you could talk a bit more about why the boundedness of gamma speed implies Ella's Lipschitz itself?
Oh, okay. Sure. Yeah. So there is a point of comparison here. I was going a little bit fast here. So I can circle. I can put a oops, I can put a box here on the left panel, and similarly here a box here on the right panel. Okay. So you see that we have always that our function L is nice. I can recall an example. L is nice, but it's super linear in the velocity v, right? And in particular, if v goes to infinity, then L is locally Lipschitz, but for velocity really large, then the Lipschitz constant depending on v, and it can go to infinity. Okay, so for example, let me give the example is that if we look at the function just Lxp is just difference of potential energy and kinetic energy, right? So this is L, right? So it's nice, but L is not global globally Lipschitz in V, and the Lipschitz constant of L blows up as V goes to infinity. Okay, so you see that if I'm not bounding the Lipschitz constant carefully, I might face the issues that, okay, all those the things are nice, uh, but because the Lipschitz constant blows up, I might not have this bound, right? So let me highlight it. I might not have the bound that the difference of L is less than or equal to C sigma times the difference of gamma and gamma dot. Um, uh, of course, one can argue that, okay, fine, although that I have certain parts of the velocity goes to infinity, but just some small parts, right? So maybe I can control the integral and stuff like that, and that's a fair point. What I'm saying here is only that if I'm using the minimizers, and because we know that we proved that the velocity of the minimizers are always bounded uniformly. So when they are bounded uniformly, when gamma dot, gamma, we are not worried, right? Gamma is in the torus, which is compact. But when gamma dot is bounded, then essentially we are just in a compact set, right? So we are only dealing with L of xv for now for x in the torus, and for v is bounded by something like uh, k sigma plus a constant in sigma or something like that. So if we are in that in that compact domain, then we have global Lipschitz property. Then we can bound everything nicely, and that's why it's important. Does that make sense?
Yeah, thank you. It does.
Yeah. So thanks for the question, and it's so you see that this is what I meant. Although I think that some of my students here, when they took some earlier courses with me a long time ago, already that there were certain points that if we are not careful with such a minimizers and with the boundedness of the minimizers, and if we just claim that, oh, it's easy, we can just control things like nicely, then things can go wrong actually in this very subtle point. So that's why I think that although that we are doing it gently, step by step, we have seen the key points of using minimizers, using that minimizers are nice, and we are only comparing things with the minimizers. So those are the essential points. Yeah. So I would say that it's really interesting. Okay. And in case that if we don't have good enough regularity of the minimizers, or if like your function L is not smooth enough, if your minimizer is not satisfying the Euler-Lagrange equations, then we have to be very careful. If we are missing any of that, doing this kind of comparison, it's dangerous. Okay. But sometimes it still works. It has to be done in a different way. Okay. All right. Great. Now I have any other concerns? Okay, so I have time for a brief discussion on the Lax-Oleinik semigroup. It's a very important subject. It's not gonna be our object. It's not gonna be done in just few minutes today. I will also introduce it more systematically in the next lecture. But I thought that it would be nice to give you a sort of a how to put it, a quick discussion about this and some magical points. Okay. So the point here is going from optimal control, what we can see here. So this is the Lux or Legnick semi-group, or as I said, this one comes very nicely from optimal control theory. So the problem is this. I'm redrawing in a bigger, a bigger picture of the text. So I have, this is the space, this is the time. Okay. So the problem in optimal control, essentially, there are many problems in optimal control. One of the problem in optimal control is the problem of, you are, starting at a given point xt in the plan. So this is your starting point. Okay. And you want to sort of go backward in time to the target. So sort of, you can imagine that, you are on a boat, standing offshore somewhere, and you want to, go, you know from that point, you would want to go somewhere to the land, whatever. So you would like to go somewhere, I mean, like, you would like to go backward in time, to reach the destination, which is any point on, on at time zero. So the point here is that, okay, so let's say that, your boat is running, going like this, going, you know back and reach the point here to y, right? That's one way to go. Or there are other ways to go, like going back like that, or, you can like go maybe straight back, or you can also go really far out, like like really far out and back. So there are many ways to go back to the point, to the um, um, to the uh, time zero. Okay, to essentially the plane Rn cross zero. So maybe, let me put it this way: you start from xt, you want to reach Rn cross zero at some point y zero. Okay. So sorry that I'm introducing it to you quite suddenly. So I'm trying to give you a shortcut sort of explanation. Anyhow, that's the goal. Okay. And as always, in certain optimizations problems, we often have to minimize certain cost functionals. And in this case, the cost functional is going to be what? So the cost functional. So what's going to be your cost, right? So the cost function are going to be two things. The first thing is going to be the running cost. It tells us that, okay, if we sort of go around and we have to pay certain price for the gasoline, or for, whatever price we have to pay, it's the running cost. And then when you hit, when you get back to the destinations, when you either land, or when you try to stop at y, you would have also to pay the so-called terminal cost. Okay? So you get to the terminal, you have to pay the terminal cost. So the two together gonna be the total cost. Okay. So the cost functional is typically gonna be, running cost is what is essentially the action functional. And in this case, we already take the minimizing one, which is h of t, right? So go from, you go from y to xt, so you pay the price ht of yx. Okay, so go from, that's the price you pay, right, for running costs. And then for terminal costs, you're given certain function g recording the terminal cost, so you pay the terminal cost g of y. For g is a given function in the torus or something like that. So an optimization problem, or a problem in optimal control, is that we try to minimize cost functional. So say uh, ht of x yx, you know, plus g of y. Okay, so you try to take minimum of y in the torus or something like that, and that's exactly the problem. So in optimal control dynamical system, we're gonna talk about that later. It's sort of really understanding the dynamical properties of this problem. But in the PD language, instead of, this is the viewpoint of Bellman, instead of looking at dynamics, you can simply define what is going to be the cost functional. You define u of xt to be infimum. I'll tell you infimum can be changed to minimum in just a minute. Y in the torus of the sum of the two, right? So ht of yx plus g of y. And you try to see if you define it like this. So this is the viewpoint of Bellman. Right? And then you try to see u is solving what PDE and what's the properties of u. Okay. Okay, so that's essentially a very interesting problem, right? We are switching gears and we are sort of introducing things and using h of t as a means interpreting the running cost, and and see what's going on. So of course we're going to discuss more about this, but I'm here to tell you like few interesting points. So few first observations. So few uh, so first some of first observations. The first thing first, that instead of writing it as an infimum, I can write as a mean. So for t greater than 0, okay, I can write this one as mean. Why is it so? G is a continuous function, right? And we have just proved that if t is strictly positive, then h of t is Lipschitz in x and y, right? So, this is just summation of two continuous functions. So infimum has to occur at some value. So that's the mean. And moreover, not just that, we can say that that there exists a point y naught in the torus and a minimizer gamma mapping from 0t to the torus with gamma 0 equals to y naught, gamma t equals to x, such that gamma is in ck, gamma satisfy the Euler-Lagrange equation, and you can write out uxt equals to g of y naught plus integral from 0 to t L of gamma s, gamma dot s ds. So it's really beautiful, right? It's remarkable that not just minimum exists, but we also have a minimizing part. So it's being realized. In other words, your optimal control problem does have a solution, right? Okay, that's the first thing. Okay. Any question on this part? Okay. Second point. Second point. Another point that is remarkable. All right. You start with something. So ux of 0 equals to g of x, which is given to be a continuous function. Okay. Now, for t greater than 0, fixed, I claim that x maps to uxt is Lipschitz. Okay. Again, the Lipschitz constant, the Lipschitz constant is less than equals to c of t, and this can blow up as t goes to 0, which is normal because you start with some initial data that is only continuous to start with, right? But instantaneously, your problem has regularizing effect. You just go up a little bit in time, no matter how much you go up, instantaneously, your problem has, you know, the u becomes Lipschitz. So that's remarkable, right? And how do you see it? Well, I mean, you just write out the definitions. You just need to use the fact that, again, minimum occur. You can just compare the values, and you just need to use the fact that ht is Lipschitz, right? ht is Lipschitz with Lipschitz constant ct. That's enough. Done deal. Okay. So that's really remarkable. So this is the so-called regularizing effect. Regularizing effect that you start with continuous function, but instant u becomes Lipschitz. Okay, so this behavior is like some kind of like the heat equation. You start with very rough initial data, but instantaneously your solution becomes C infinity, for t small enough. Again, the constant, the smoothness constant might blow up as t goes to 0, but that's a remarkable point. Again, details will be coming more and more, but I just want to throw out certain points, and um, Lipschitz property and stuff like that we're going to prove later. I just throw to you certain points to start with. Okay, so the last point I want to throw out is a so-called dynamic programming principle for you. So dynamic, and we already proved it, so that's why it's beautiful. Okay, so it goes like this. I can just draw a picture and tell you. So if I go from, this is time 0, this is time t, this is time t plus h. So let's say I start at a point, what, here. So this is a point x t plus h, and I want to go back in time, right? Going to a point y here. And the problem about optimizations essentially says that if I want to be optimal, then I should be always optimal. And that's essentially the way that people phrase about dynamic programming principle, but I can just write down. So I have ux t plus h equals to minimum, fine, y of g of y plus h of t plus t prime of y to x. Okay, now I'm using the earlier part that we already said about not t prime, t plus h, about connecting the two, right? So this h of t plus h can be written as infimum can now becomes minimum. So this is minimum of z in the torus of h of y to z first, and then h of o. I have H. Okay, forgive me. I have two H here, but okay, now I'm out of town, so I'm just gonna abuse my notions. So forgive me on this. Well, okay. Yeah, I'm not happy. So let me change it to sigma. Yeah, I didn't, I didn't pay attention to this. So let me change it to sigma. Sigma, sigma here, and then I have t plus sigma is sigma, sigma. Okay, fine. So now it's less confusing. All right. So you see that it's beautiful that I can write, break it into the mean, right? And then this allows us to write that ux t plus sigma equals to mean of yz. Let's just pull it out first, and then I'll put it back later. G of y plus ht of yz plus a sigma of zx. Okay. Now I'm going to take mean over y first here, right? So this equals to taking mean over y. I'm just going to have mean of z out here. Mean over y of this one, by definition, this is nothing but u of xt plus h of sigma zx. Sorry, not u of zt. Okay. So that's exactly the dynamic programming principle. I'll just explain it in the picture and done with the lecture today. So what I'm saying here is that once you have an optimal part, it has to be optimal all the way. So what it tells us is that in, uh, you know, um, so, you have sort of the point x t plus sigma here, right? You want to go backward in time. What it tells, the dynamic programming principle says that, okay, you don't need to go backward in time for all time, but you just go back for an amount time of sigma, then you would reach to the point here is probably zt, right? And the dynamic programming principle says that to go back to the point zt, it has to also be optimal, right? So you have exactly the same formula, like the formula for u, but you just go back from the time t plus sigma to t, and that formula is being preserved fully. And this formula, if we use it smartly, later on we can derive that from this formula. We're going to see that U is a viscosity solution. I just throw out the word. We do it later. Solution to the PDE Hamilton-Jacobi equation, which is exactly UT plus H of X. The U equals to 0 in Tn cross 0 infinity, and U of X0 equals to G of X. Okay. Again, this is for much later. I just want to throw out the point, and you see that using HT, we can do a lot of stuff. So that's why it's a fundamental object. Okay, I'm sorry, I'm a bit over time today. Any quick question, or else we can conclude. And this is sort of the end of the first half of the semester, and I'm happy that so far not yet any technical glitch. Hopefully. Hopefully there will be none. I don't know. I mean, there's no warranty, but we are not worried about winter storms or anything, so far. Okay, so no questions. Thank you all. And you see that again, although things are very simple, but once you connect the dots, there are a lot of beautiful things. And I hope that you see this big picture. It might be helpful one way or the other in your work. I don't know. Maybe not, maybe. But at least it's beautiful. Okay. So thank you all, and have a great weekend again. Stay safe and healthy. Meanwhile, still, trying to sort of, get some fresh air and stuff like that, whatever takes. Okay. Thank you, and see you later. Bye for now. See you.